Last Thursday we discussed ketones. We've been working on the class 2 carbonyls. We are now going to move into the class 1 carbonyl. And so we'll get into carboxylic acids. We'll talk about how to name them. We'll get into some of their properties, particularly pH, because carboxylic acids are going to deprotonate on that hydroxyl group depending on what the pH of the environment is. Okay? And carboxylic acids are a major component of amino acids. That's where it gets its name. It has an amine group, a carboxylic acid group. And depending on the pH of the body, which is pretty stably 7.4, that's going to either have it deprotonated or in its protonated form. And so oftentimes it's written in the deprotonated form, so it would be our amine group here, and then with a minus there, okay, because in physiological pH, it's often in that form there, okay? And then probably Tuesday we'll get into how we make carboxylic acids. In some cases it's similar to ketones. Ozonolysis we'll use as one technique. And then going backwards, so going from carboxylic acids to the things that we derived from in the first place, and looking a little bit at equilibrium, and so which will be favored at depending on what kind of groups are on there and how reactive they are. Okay, so when we talk about carboxylic acid derivative, we're talking about what are we using to make that carboxylic acid, and then depending on, again, how reactive the carboxylic acid is versus the derivative at equilibrium, which way is going to be more favorable. And of course, with Le Chatelier's principles, we can coax it to one side or the other based on tweaking things like temperature, pressure, things like that. All right? All right, so we've been talking about aldehydes, then we talked about ketones, and those are the class 2 carbonyls. The class 1 carbonyls, which we'll talk about today, carboxylic acid, is going to be those that have a good leaving group, all right? So, that makes it easy to deprotonate because that hydrogen is going to be considered a good leaving group. And so because it has good leaving groups, it's going to undergo substitution reactions, right? Where the nucleophile attacks and the leaving group leaves. All right, and here are some examples. Acetic acid, right? That's essentially vinegar. That's a byproduct of fermentation for certain microbes. So yeast is going to predominantly break down sugar into carbon dioxide and ethanol, but certain bacterial species will break it down into carbon dioxide and acetic acid. Other ones will break it down into lactic acid. And so that's where things like sourdough come into place. The sour aspect of that bread is due to the bacteria, okay, that is in that culture. Butyric acid. So butter is a fat, right? It's a lipid. It's a saturated lipid. And it's going to have a non-polar head and then a polar tail, which is the hydrocarbons, right? And this is going to be the non-polar head. And if it starts to break down into butanoic acid from the ester that it has, break down from an ester into this, and that's how sometimes butter can go bad. If it sits out too long, it's just breaking down.
It's microbes that break it down?
Not so, I mean, it could be microbes doing that to some extent, and it could also just be temperature. So if you leave it in the refrigerator, it's not going to go bad. But if you heat it up, just even at room temperature, then it will start based on, again, what other things are in that butter that drive it toward the either derivative or the acid, it'll break down. Okay. So it's just kind of a degradation product of that fat breaking down. Hexanoic acid, my 12-year-old has a lot of hexanoic acid right now. He just stinks all the time. Lactic acid, right? So when your milk goes bad, that is usually from microbes breaking it down into lactic acid. If you are undergoing anaerobic respiration, you're going to start producing lactic acid, and that's partly why your muscles are sore afterward. In addition to just tearing muscle fibers, you're also just building up a lot of lactic acid. What else do we have on here? So acetyl salicylic acid, you did a lab. Did you do a lab where you made aspirin with salicylic acid?
I think we did that.
Yeah.
Yeah.
I remember Sean talking about a lab like that, but I don't think we ever did.
Yeah.
Okay. Pretty straightforward, very common lab. I think I mentioned, I believe that's what I was doing during 9/11. We were making aspirin. Just because you get a nice, big, fluffy yield from it. So,
What do you start with for that?
what's that?
What do you use for that?
Acetic anhydride and salicylic acid. And then you essentially turn it into, so the acetyl anhydride, it tacks on this acetyl group here to convert it. Salicylic acid is in plants, and in particular the bark of a willow tree. Native Americans used to chew on the bark, and they realized that it had pain-killing properties. Salicylic acid by itself is a little hard on the stomach, so that's why they converted to this acetyl salicylic acid, or commonly called aspirin. It's a little bit less harsh. And then other medications, right? Yeah. There's also formic acid. So, did I put that on here? Oh, yeah. So formic acid is the simplest, right? It's got, instead of an R group on here, it's just got a hydrogen. And that is what is essentially in ants. So if you've ever squished an ant, you might notice it has kind of a acrid or sweet aroma to it. That's their blood. And formica is Latin for ant, because this was first isolated from ant blood.
They use that in their for like their circulatory system.
Yeah. Yes. So that's why formic acid got its name. Yeah. And these are obviously common names, right? So if we were to give it the IUPAC name, it's going to be oic acid, right? And so 1, 2, 3, 4. That's bute. So butanoic acid. Here it's going to be 1, 2, 3, 4, 5. So pentanoic acid. And of course, you add in your substituents. But because a lot of these common names are relevant in biochemistry and biology, we use these common names a lot. So formic acid, acetic acid, propionic acid, or propanoic acid. Those are two interchangeable names. Propionic is a pre-IUPAC nomenclature, and so it's just kind of stayed in there. But if you see propionic, just know that that means propanoic, and then butyric would be butanoic acid, right here. Right? So same thing, just this came before IUPAC. And then benzoic acid would be essentially I think it's benzene carbaldehyde. Carbaldehyde is that. What is the IUPAC name? I only call it. This is one where I only call it benzoic acid. It's like benzoic. Maybe it's benzene aldehyde. Maybe it's benzene aldehyde. Yeah. But by and large, anywhere you see this molecule, it's going to be referred to as benzoic acid. It's even an IUPAC. And then down here, right here, if we deprotonate this, so we remove that hydrogen there, like I drew up there, then it's going to be 8. So butanoic acid would be butanoate. And this may be familiar if you go back to the days in Gen Chem. So if an acid ended in ic, it must have come from an 8, right? And if an acid ended in us, it must have come from an ite, right? And so if we had SO4, that is sulfate or sulfite?
Sulfate.
Sulfate. If we have H2SO4, we call that sulfuric acid, not sulfurous, right? So we're staying with that nomenclature, and therefore all of these things are ic, right? Formic, acetic, propionic, butanoic. So if we deprotonate it, we just are essentially going back to that 8 suffix. Right? Questions so far? Comments?
Kind of one's not really direct though, because I was thinking like they use hypochlorite to for water, to kill microbes. I was just kind of wondering like what on the microbe is that, like what reaction does that do? Or...
It's the chlorine.
Mm-hmm.
So chlorine is very reactive, and so it starts attacking the molecules in the membrane that make up that microbe.
Yeah.
And so anytime you change a molecule by adding something or taking something away, you alter it, and it's not the same. And so, so chlorine is a good one, particularly for water and stuff. You wouldn't want to put chlorine on your skin, although we go into hot tubs and pools and stuff with chlorine in it. But if you remember the reactivity, so fluorine, very reactive, then chlorine, then bromine, then iodine. So usually in hot tubs and pools, they'll use chlorine or bromine.
Oh yeah.
And bromine is kind of considered a safer alternative because, again, bromine is not as reactive as chlorine, so it's not going to attack your skin as much. And then iodine is used as a topical antiseptic, right? And that's because iodine is the least reactive. It's going to still react with the microbes on your skin, but your skin is somewhat protected by a layer of dead skin cells. So same thing with hand sanitizer that has usually ethyl alcohol or propyl alcohol, and what that does is that breaks down the membrane of microbes. But why doesn't it break down the membrane of our skin? Right? It would. That's why it burns sometimes if you have a cut. But your epithelial cell layer has a pretty much an armor of dead skin cells. They're constantly coming off, and so that kind of is a protective barrier between you and whatever you're treating the microbes with.
Okay. So it's really just opening up that membrane and letting the insides out.
With alcohol, yes.
Yeah.
With halides, what they do is they are highly reactive, and they will attach as like a nucleophile and then alter the structure of the molecules, and then prevent things like protein synthesis. You need to have protein. You need to make proteins to stay alive. And it does it pretty quickly. And in pools and stuff, it's diluted enough that you can swim in it.
So being attached to like oxygen as like a chlorate, is that, or yeah, I think it's chloride, right? Like HO. Is that, does the oxygen like help that, or?
No, it's just the delivery system.
okay.
Really.
Yeah.
Okay. Because chlorine by itself is a gas.
Yeah. Okay.
Right. So you can use, you can bind it to oxygen, turn it into a solid if you want, or dissolve it into a liquid solution like bleach. Right. So hypochlorite is bleach. Sodium hypochlorite. Right. And so that's just essentially allowing it to exist in that liquid. So when you add it, then the chlorine can come off and attack the.
Okay. Yeah, makes sense. Cool.
Good question. And kind of to that, after this slide deck, I'm thinking we'll probably talk a little bit about amines, and then dip our toes into the more biochemistry side of organic chemistry, if that's okay.
Yeah.
I feel like we're all more into biology, right? So
It's cool to see how the chemistry applies. Like, so.
yeah. I mean, it'll be OChem, but just in the context of nucleic acids, carbohydrates, proteins, and lipids. Sound good?
Yeah.
Okay, so how do we name these? And you might want to have your other sheet kind of handy, so we can provide both the IUPAC and common name for these. So if we have two carboxylic acid groups, then that is, oh, I see, sorry, I skipped something. Now it's gonna make more sense. Dioic, all right? So pentane, you're gonna count the longest chain, 1, 2, 3, 4, 5. So it's gonna be pentane dioic. Or oftentimes that E gets dropped, it's pentane dioic. All right? Here are some examples of common names often used in biochemistry. So glutaric acid is going to have 1, 2, 3, 4, 5. Succinic acid, 1, 2, 3, 4. Malonic acid, 1, 2, 3. And oxalic acid, 1, 2. And we could also call that ethane dioic acid. Propane dioic acid, right? This would be 1, 2, 3, 4. Butane dioic acid, and this is this. Right? So pentane dioic acid or glutaric acid. So then going back to this part, right? We have how many carbons? We have 1, 2, 3, 4, 5. So what would that be?
Pentane dioic acid.
Yeah, it's this one right here, right? And so the common name would be glutaric acid, iupactane pentane dioic acid. B, we just have one carboxylic acid group, right? So it's 1, 2, 3, 4. So what was 4?
Butane dioic acid.
Butane. Not,
Oh,
yeah,
dioic,
butanoic, right?
Butanoic, yeah.
Butanoic is just one. Butanoic acid. And then what did we say 4 was? Succinic.
Okay. Yeah.
Okay. Glutaric acid is also what is used to form tartaric acid, which is in tartar sauce. We also use tartaric acid in baking powder. So you know, as a chef, you probably know that, or I don't know, maybe you're a chef, not a baker. Those things are kind of different.
A little
Do
bit. I
you
have to
do
make
both?
pizza dough later.
Right? Okay.
Yeah.
But you know, baking soda and baking powder are different things. Baking powder is essentially sodium bicarbonate, which is baking powder, but it also has tartaric acid in it. So it has the acid mixed in, so that when you add water, it can undergo its reaction and create bubbles, right? Carbon dioxide to lemon things. Baking soda doesn't have the acid. That's why when you make the volcano, you know, the 3rd grade
Gotta
science
get vinegar.
project, you add vinegar. You have to add the acid to it. So if you're ever in need of baking powder and you only have baking soda, then you can add some what's it called, cream of tartar. That's it's a powdered spice.
I thought they use the tartaric acid for like wine making too. Are you familiar with that?
They do, yeah, exactly. It comes cream of tartar comes from the wine making process using the tartaric acid, and it's just like a byproduct that they don't use, and then they will often then just take that and repurpose it.
Okay. That's
Yeah,
actually
absolutely.
cool.
Oh, this something's weird about this keypad. It keeps skipping things. All right, here. So C6H5. When we see that, we see benzene, right? So benzene with carboxylic acid group, that's going to be what?
Benzoic acid or
Yeah. Benzoic acid. And then, what did I say the IUPAC name was? Benzene. Did I say benzene aldehyde? That wouldn't be right. Because it's not an aldehyde. Benzene carboxylic acid. Yeah. Benzene carboxylic acid. Or benzoic acid, common. All right, I'll let you do D through F together or on your own, however you prefer, and then we'll go over it. still working? Yeah? Okay. D. 2 carboxylic acid, so it's going to be a dioic acid. And then we have 1, 2, 3, 4.
Butene dioic acid.
Yep. Butane dioic acid, or yep. E is going to be 1, 2, right? So we could call that ethanoic acid, or we could call it acetic acid. Okay, so acetic acid would be the common name. Ethanoic acid, IUPAC. And then this one, that's going to be essentially formic acid. Anybody, do we have it in here what the, I don't think I put it in here, but
Would be methanoic.
methanoic, right? Because that's just, if 2 carbons is ethanoic, just one carbon, methanoic. All right, so structures, let's see here. How do we do that? Cyclobutane, so that's gonna be 1, 2, 3, 4, right? Carboxylic acid, just kind of like how benzene carboxylic acid was a benzene ring with the carboxylic acid. Now it's just a cyclobutane with carboxylic acid. B, 3,3-dichlorobutyric. Okay, so but, 4, right? So 1, 2, 3, 4. And then we have 3, 3. 1, 2, 3. And in case I didn't cover this, I think I did with aldehydes and ketones and stuff, but we always number starting with the carbonyl. So 1, 2, 3, and what is it? 3,3-dichloro. All right. And then 3,3-dimethyl glutaric. All right, so now they're throwing in some common stuff. We go back. Glutaric is pentanoic acid. All right, so 1, 2, 3, 4, 5, and 1, 2, 3. Got it.
Wouldn't it be the diacid for glutaric?
Sorry, which?
For C.
Oh, yeah, you're right.
Oh, it's 2
So,
on each side.
Yep. Good call. Wait, 1, 2, 3, 4, 5. So then, thanks for that catch. That's a dioic.
Yeah, the common name doesn't really like emphasize that it's a dioic. I
No.
remember that. Yeah.
That's why I don't like common names, you know, because common names you just have to memorize. IUPAC, you don't have to, once you memorize the prefixes and stuff, and the suffixes, you can always put it together. I'm sure glutar has some, Latin derivation that is used, just like formic comes from ant, but has nothing to do with, nothing about this screams out ant to me, right?
Yeah.
So that's the problem.
It had a name before they knew the structure for those. Then. Yeah.
Well, or again, back then it was kind of like, we have our solar system. We name it after Roman gods, and then we start finding more and more planets. It's like, God, we can't come up with like new names for all of this stuff. We have to have some systematic way, and that's why now we have these very boring names for planets in the distance. It's some combination combination of letters and numbers
Oh, yeah.
because there are so many out there that you're gonna run out of words to describe it, and it won't give you a position of where that planet or that star or what have you, whatever celestial body is located. Same thing with these, like these molecules. Organic chemists started finding the simple ones first, the low-hanging fruit, and then realized, oh my gosh, there are millions of these. We got to come up with some way, but they didn't for a long time. They just kept naming them, you know, based in Greek and Latin, and then finally, that's why IUPAC is so awesome. You know, like learning it at first is kind of like, God, this is anal retentive, you know. But once you learn it, you learn to appreciate it. Right?
It's not ambiguous. Yeah.
All right. So erase these. Let's do this last problem now. Provide the name for the following. So if you've already done this, stay tuned. If you haven't, name these two and see what you come up with. Starting at the carbonyl, 1, 2, 3, 4, 5, 6, right? So only one, so
Hexoic acid.
yeah, cenoic acid. And then we have 3, right? 2 methyls on the third carbon, 4, oops, can't fit it in, tetramethyl hexanoic acid.
You got 2-propyl pentanoic acid.
So this could be a little bit tricky, right? Because technically, that's the longest chain, right? 1, 2, 3, 4, 5, 6, 7. But we always start from the carbonyl, so it's going to be that, right? And so in that case, we have 1, 2, 3, 4, 5. So pentanoic acid. And you said 2 propyl. Pentanoic acid. What if I got rid of that H? Pentanoate.
Pentanoate.
O8. All right. Cool. So pretty straightforward stuff, right? I mean, you guys are naming experts by this point. I had a midterm in my intro to OChem and biochem class, and so now we're shifting gears into biochemistry. So the first half of the quarter is OChem, the second is biochem. I'm hoping there'll be a little bit less deer in the headlights. It might just be the nature of the students, but they do seem a bit overwhelmed with OChem. So we'll see. Biochem is OChem, but you use what you know in OChem to then apply it to the structures of biochem. We'll see. All right. So, carboxylic acids have strong intermolecular forces. So, reviewing intermolecular forces, dipole, that's the simplest, right? Where just at any given moment, electrons are going to be disproportionately located on one side of the atom. And so it's going to be attracted to another molecule that has electrons disproportionately on the other side as well, and will form a brief intermolecular attraction to each other, right? Anybody remember another one? Another intermolecular force?
Definitely water.
Or
Force of like van der Waals.
Van der Waals, yep. So, dipole, van der Waals, dipole, ion dipole, like so anything with charges, opposite charges, okay, and then there's hydrogen bonding. And hydrogen bond is a really strong intermolecular force because that's what keeps our DNA together, essentially. It's not a covalent bond, so it can be broken. It's not a bond at all, really, it's just an attraction. And so that's what gives proteins their structure, how they go from a long peptide into some specific conformation. It also means that we can take those two strands of DNA, right, and pull some of them apart to transcribe and do gene expression, right? Or we can rip the whole thing apart and copy it for cellular division. Right? So hydrogen bonds are a nice Goldilocks in that they're strong, but they're not covalently strong. Right?
They're easy to like do and undo.
Yes, with the proper amount of heat, right? Or other things. But if you look at carboxylic acids, what do we have? We have not just one oxygen that can form hydrogen bonds, but we have two. And by nature, unless it's deprotonated, it's going to have a hydrogen on it. So the hydrogen on this hydroxyl group is going to hydrogen bond with the carbonyl oxygen, and then vice versa. Okay? And so if you look at two molecules that are very similar in size, right? Ethanol versus acetic acid. Look at the boiling point. The boiling point is going to be a lot higher than ethanol. Okay. If we were to look at benzene, I don't remember what benzene's point. I think it's around 80. No, yeah, 80, so 80.1. 80, right? If we were to take that put a carboxylic acid group on there to make it benzoic acid. Uh, 121 to 123, right? So we didn't add too much to that, right? but we have now two oxygens forming those hydrogen bonds. What if we took benzaldehyde? Remember that only has one oxygen. We could suppose that that might be somewhere in between, right? Because it has some degree of hydrogen bonding available, but not as much, right? So benzaldehyde. $179.
I think the first one was the 120 might have been the melting point for the benzoic.
I'm sorry, what was that?
Oh, because that last one it said melting point and.
Oh, I wrote down the melting
I think,
point, didn't I?
yeah,
Yeah, that
and
makes
then-
sense because we've done that in lab, right?
You're right,
We've-
yeah.
Yeah, okay.
I
So,
think the boiling point is
boiling
like
point,
170.
we're doing boiling points, right?
I think so, yeah.
Because benzene is a liquid. And melting points will be different too. Okay, that was the boiling point of benzene. The boiling point of aldehyde is 179. And then let's go back. What? Yeah, 240.
240.
That makes more sense.
Oh, cool.
To basically 240. Right? So as we add more oxygens, we give it more opportunity for hydrogen bonding, and we make it more and we make it so that we need more heat to break it apart. Okay. So there's that is one of the properties of carboxylic acids. The other is acidity, right? So again, if we have a carboxylic acid and we have a certain pH in the environment, it can kick off that hydrogen. And it can do that readily because we can have a resonance. This pi bond can resonate back and forth between those two oxygens located on that same carbon to stabilize that structure. So it doesn't need that hydrogen as much because it has resonance stabilization. And so this is just showing it deprotonated, right? But what we could do is we could have a resonance structure. It's like this, right? And it just jumps back and forth.
So the resonance structure makes it more easy to kick off the hydrogen, or for that to be taken?
Yeah, because it can get by
Okay.
based on the resonance. Just like how benzene itself is so darn stable because of the resonance,
Okay.
right? This is resonance stabilized. If this was an aldehyde, you couldn't take off that hydrogen as readily. You couldn't deprotonate it as readily. You can still do it, right? But because now this carbon's going to have a positive charge on it, right? So the resonance says, "Oh, okay, I can kick that off. I've got stability in that bouncing back and forth." All right. Now, pKa. You guys remember pKa? pKb, Ka, right? Acid dissociation constant. Right. Let's have a little review on that. pKa between 4 and 5. That's going to, in the context of electron donating groups, it's going to increase the pKa, thus decreasing acidity. So high pKa equals high pH. The lower the pKa, the lower the pH. So if we're increasing pKa, we're increasing pH, and so the acidity is going to go down. So it's a little bit confusing because we're talking about up and down, but you want to think about it just not in acidity, but just in context of pH. That's the relationship. Conversely, in this range, right, if we have electron withdrawing groups, those are going to decrease the pKa and increase acidity. So they're going to bring the pKa down. Low pKa gives us low pH. Or low pKa means that the acid is going to dissociate and kick off those hydrogen atoms, because that's what pH is, right? P is just a function for a log, right? So pH is the log of the hydronium ions, or hydrogen protons, you can think of it that way, right? But the more acidic something is, the more likely it's going to kick off its proton. It's going to deprotonate. And then that proton is then going to bind to the water in that solution to form H3O, right? And so because these can be large, somewhat large numbers, we take a log. In this case, log is base 10. Right? So we just compress those numbers down to a scale of 1 to 14. Oh, these are not in HR. Dude, I had some guy, Andy, I think was his name. Yes, Andy. When he was supposed to add a color printer, we have a color printer in there, and he added all kinds of printers to my thing, but not the color printer.
Oh no.
And now I don't know, they're all named very similarly. So I did print something, I was like, I guess that never showed up. So I just printed it to another one of my printers. Thank you, appreciate it. So log base 10, right? Compressing that down. And so if you look at these different compounds, some of them are going to be more acidic than others, right? So this benzoic acid, in the grand scheme of things, has a relatively high pKa, right? This is acetic acid. This is vinegar, right? We can drink vinegar. I mean, some people actually drink it straight,
Apple cider, yeah.
right? Apple cider vinegar. But we put it in a lot of things, right? It's not so low that it's going to harm you, right? If you drink too much of it, it's not great. But this pKa range is physiological, right? Once we get further down into it, though, we're starting to add chlorines, and look what it does. It drops that pKa way down, and thus the pH is very low. And so if you have a lot of electron density, the proton is going to want to stick on to that carboxylic acid group. When you get rid of the electron density, how do you get rid of electron density? By having electron withdrawing groups, right? Then we're more likely to deprotonate. Okay. So, with that in mind, this, with that pKa of 0.9, is going to be pretty much as acidic as like hydrochloric acid. Hydrochloric acid, pH of 1, very acidic. That chlorine facilitates dissociation of the proton very readily. Here we have all, look, if you, sorry, here. The more chlorines we add, the lower the pKa gets. Electron withdrawing. You remember Henderson-Hasselbalch?
Hasselbalch-Euclid equation.
Vaguely.
Yeah.
All right, so essentially we can say that pKa equals pH. All right? And so we could also say that the deprotonated form of a carboxylic acid equals the protonated form. We can also write this relationship of pH and pKa as pH is equal to pKa, or essentially the log of hydronium ions is equal to the log of Ka plus the log of a ratio, okay? A concentration. That concentration or that ratio is the conjugate base over the acid. Okay? So you may remember that HA just depicts a protonated acid. A is for acid. H minus means that acid has been deprotonated. Okay, so we could write it, you know, if we were looking at carboxylic acid, we could write, you know, this form. Whatever that concentration is, over this here. Right? That would be A minus, that would be HA. Now, we can further simplify this by getting rid of the function, getting rid of that log, right? And doing a little bit of algebra. If we take away the log from everything and rearrange the K, so that if we take away the log, then we have H, Ka, and A minus over HA. Right? This being essentially hydronium, right? So we can write this as H3O. And if we wanted to rearrange this, we could just say that Ka is equal to the acid, or I'm sorry, the conjugate base, hydronium, and HA. So, how do we apply this? All we really need to do is, if we're given pH and the pKa, we can determine what this ratio is. And that will tell us for every, depending on what the ratio is, for every one conjugate base, or for every one deprotonated version, how many protonated versions do we have? Or vice versa, right? So if the pH of the environment is different from the pKa of the molecule in it, that will change whether or not it's going to be in its protonated form or its deprotonated form. Alright? So what you need to know there is that if pH is less than pKa, pH is less than pKa, those hydrogens are going to want to stick around. And if they stick around, what form is going to predominate? Protonated or deprotonated?
Deprotonated.
They're going to stick.
Oh,
I guess they're going to stick around on the molecule,
Yeah.
so it's going to be
Protonated.
protonated. If pH is greater than pKa, hydrogens leave. We get deprotonated. There are fewer hydrogens around because pH is high. So again, if the pH is high, they're going to hold whatever that solution is going to hold on to those hydrogens more readily than if the pH is low. Okay? And so that's the relationship between pH and pKa. So for this, acetic acid was dissolved in a solution buffered to a pH of 5.6. What is the ratio of concentrations of acetate ion and acetic acid? And which predominates? So remember, if we deprotonate something, we just put 8 on it, right? So an acetate ion is acetic acid without that H. So acetic acid acetate, and we want to find out what is going to be predominant. So what do we give it? 5.76 pH pH equals 5.76. We have the pKa in one of these slides here. Here, right? Acetic acid, pKa, 4.76. Doubt that they picked a pH of 5.76 by accident, right? Because what can we do? We can say that 5.76 equals 4.76 plus the log of A over HA. All right? And we can subtract the 4.76 away from that right side to get the log of conjugate base over acid by itself. And when we do that, what's 5.76 minus 4.76? 1. So 1 equals the log of, running out of room here, these concentrations. Now, we want to get rid of that log. So, this log, in this case, with pH, the pK is base 10. So if we take it to the 10th power, if we take 10 to that power, or 10 to the power of this, we wipe out that log. And whatever we do to that side, we do to the other side. So if we took 10 to the log of this whole thing, that equals 10 to whatever this is, in this case 1. 10 to the 1 is 10. 10, a base of 10, 10 to the base of 10 is 1. Okay? So we're taking something, essentially when we write log base 10, we write 10 as a subscript, right? You can kind of think of it as the same way of, you know, what's 6 over 6? 1. What's a subscript over a superscript? 1. Okay. So we end up with canceling that out. 10 to the base of 10 is 1. So what this all means is that 10 equals H minus over HA. That's the ratio. So for every protonated version, right, every acetic acid we have, we're going to have 10 deprotonated acetate ions. And that's going to predominate, right? We're going to have more. We're going to have 10 times as many acetate ions as we would acetic acid. If we then took this pH, started lowering it, then we'll start changing that ratio, right? And we'll start getting more of the protonated form, right? But in this case, the pH was higher than the pKa, 5.76 versus 4.76. And so, we had to make sense? Yeah? Okay. You didn't think you'd have to do math. Just a little bit, just a little bit. Okay, let's take a break. 11:10, let's come back at 11:20.